Right now, at this very moment, as you sit there watching this video, you are hurtling through space at an absolutely ridiculous speed. The Earth beneath your feet is spinning at roughly 1,670 kilometers per hour at the equator. But that is nothing. The Earth itself is orbiting the Sun at about 107,000 kilometers per hour. And the Sun, along with our entire solar system, is whipping around the center of the Milky Way galaxy at approximately 828,000 kilometers per hour. And if that were not enough, our entire galaxy is rushing through the cosmos at about 2.1 million kilometers per hour, relative to the cosmic microwave background radiation. You are moving at incredible speeds right now, and you do not even feel it. But here's the thing. All of those speeds, as mind-boggling as they are absolutely pathetic compared to the speed of light. The speed of light is so fast, so incomprehensibly quick, that it makes everything humanity has ever built. Every rocket we have ever launched, every probe we have ever sent into the depths of space, look like a snail crawling across a highway. The speed of light is 299,792,458 meters per second. Let me say that again because I want it to sink in. 299,792,458 meters every single second. That is roughly 1.08 billion kilometers per hour. At that speed, you could circle the entire Earth 7.5 times in a single second. You could travel from the Earth to the Moon in about 1.3 seconds. You could reach Mars in as little as 3 minutes when it is closest to us. You could get to Jupiter in about 35 minutes. You could reach the edge of our solar system in a matter of hours. Light is the fastest thing in the universe, and as far as we know, nothing that has mass can ever reach that speed. But what if it could? What if, somehow, through some incredible breakthrough in technology or physics, we managed to build a spacecraft that could accelerate all the way up to the speed of light? What would actually happen? Not in some vague, hand-wavy science fiction way, but actually, physically, according to the real laws of physics as we understand them. What would happen to you, to your body, to your spaceship, to time itself, to the very fabric of space around you? What would you see? What would you feel? Would you even survive? And if you somehow did reach that impossible speed, what would the universe look like from your perspective? These are the questions we are going to answer today, and I promise you the answers are far stranger, far more mind-bending, and far more beautiful than anything science fiction has ever imagined. Because the truth is, when it comes to the speed of light, reality is weirder than fiction. Much, much weirder. In this video, we are going to take you on a journey. We are going to start from a standstill and accelerate, step by step, all the way up to the speed of light. We are going to explore what happens at 10% of light speed, at 50%, at 90%, at 99%, at 99.99%, and finally, at the full, impossible, mind-shattering 100%. We are going to dive deep into the physics of Einstein's special relativity, into time dilation, length contraction, relativistic mass increase, and the strange visual effects that would assault your eyes as the universe warps and twists around you. We are going to talk about what happens to your body, what happens to your perception of reality, and what happens to the very concept of time and space themselves. We are going to explore the paradoxes, the impossibilities, the loopholes, and the tantalizing possibilities that scientists are exploring right now in labs and on chalkboards around the world. And at the end, I am going to share with you one final, extraordinary fact about light speed that will completely change how you see yourself and your place in this universe. So, If you're the kind of person who lies awake at night, wondering about the mysteries of the cosmos, if you are the kind of person who wants to understand not just what the universe is, but why it is the way it is, then this video was made for you. Hit that like button right now, subscribe to this channel if you have not already, and turn on the bell notification because you do not want to miss what comes next. Drop a comment below telling me what you think would happen if we reached light speed, and let us see how your prediction compares to what the physics actually says. Now, let us begin. To truly understand what would happen if we reached light speed, we first need to understand what light speed actually is, and the story of how humanity figured it out is one of the most fascinating tales in all of science. For most of human history, people assumed that light traveled instantaneously. When you light a candle, the room seems to illuminate immediately. When you see a flash of lightning, it appears to happen all at once. The idea that light had a finite speed, that it took actual time to travel from one place to another, seemed absurd to most people throughout history. Even the great Aristotle believed that light was instantaneous. And for a very long time, nobody could prove him wrong, because light is just so incredibly fast that with the tools available to ancient and medieval scientists, there was no way to measure it. The first person to seriously try to measure the speed of light was the great Italian scientist Galileo Galilei, way back in the early 1600s. Galileo came up with a clever experiment. He and an assistant each stood on hilltops about a mile apart, each holding a lantern with a shutter. Galileo would open his lantern's shutter, and the moment his assistant saw the flash, the assistant would open his own shutter. Galileo would then try to measure the time it took for the light to make the round trip. But of course, this experiment was doomed to fail. Light covers a mile in about 5/millionths of a second. There was absolutely no way Galileo could measure a delay that tiny with the instruments of his time, or even with his own human reaction time, which is roughly a quarter of a second. All Galileo could conclude was that if light did have a finite speed, it was extraordinarily fast. He was right about that, but the actual number eluded him. The first real breakthrough came in 1676 from a Danish astronomer named Ole Rømer. Rømer was studying the moons of Jupiter, specifically Io, the innermost of the four large Galilean moons. Io orbits Jupiter every 42.5 hours, and it regularly passes behind Jupiter, disappearing in an event called an eclipse. Astronomers could predict exactly when these eclipses should happen based on Io's orbital period. But Rømer noticed something strange. When Earth was closest to Jupiter in its orbit around the Sun, the eclipses happened a bit earlier than predicted. And when Earth was farthest from Jupiter, the eclipses happened a bit later than predicted. The difference was about 22 minutes. Rømer realized what was happening. When Earth was farther from Jupiter, the light from the eclipse had to travel a greater distance to reach us, and that extra distance caused a delay. He used this observation to calculate the speed of light, and while his estimate was off by about 26% compared to the modern value, it was a monumental achievement. For the first time in human history, someone had demonstrated that light had a finite speed and put a number on it. Over the next 2 centuries, scientists refined the measurement using increasingly clever techniques. In 1729, the English astronomer James Bradley used a phenomenon called stellar aberration, the apparent shift in the positions of stars due to the Earth's motion through space, to calculate a more accurate value. In 1849, the French physicist Hippolyte Fizeau used a rapidly spinning toothed wheel to directly measure the speed of light over a terrestrial distance for the first time. He sent a beam of light through a gap between the teeth of a spinning wheel, bounced it off a mirror about 8 kilometers away, and measured whether the returning light made it back through the same gap or was blocked by the next tooth. By adjusting the rotation speed of the wheel, he could calculate how fast the light was traveling. His result was remarkably close to the modern value. Then, in 1862, another French physicist, Léon Foucault, the same man famous for the Foucault pendulum that demonstrates Earth's rotation, improved on Fizeau's method using a rotating mirror instead of a toothed wheel. And in 1887, the American physicist Albert Michelson, who would later become the first American to win a Nobel Prize in physics, conducted what is arguably the most important experiment in the history of physics. Together with the chemist Edward Morley, Michelson designed an experiment to measure how the Earth's motion through space affected the speed of light. At the time, physicists believed that light traveled through a medium called the luminiferous ether, a sort of invisible substance that permeated all of space. If the ether existed, then the speed of light should change depending on whether you were moving through the ether or against it, just as the speed of sound changes depending on whether you are moving with or against the wind. Michelson and Morley built an incredibly sensitive instrument called an interferometer that could detect even the tiniest differences in the speed of light in different directions. They split a beam of light into two perpendicular paths, bounced each beam off mirrors, and then recombined them. If one beam traveled faster than the other due to the Earth's motion through the ether, the recombined light would show an interference pattern. They ran the experiment at different times of day, different times of year, in different orientations. And the result? Nothing. Absolutely nothing. The speed of light was exactly the same in every direction, no matter how the Earth was moving. There was no ether wind. The speed of light was constant. This result baffled physicists. It seemed to make no sense. If you are in a car going 60 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the side of the road sees the ball moving at 80 kilometers per hour. Speeds add up. That is basic intuitive physics. It is what Newton's laws predict. But the Michelson-Morley experiment was saying that this did not work for light. If you are in a car going 60 kilometers per hour and you turn on your headlights, the light does not travel at the speed of light plus 60 kilometers per hour. It just travels at the speed of light. Period. No matter how fast you are going. No matter what direction you are moving, the speed of light is always the same. 299,792,458 meters per second. For nearly 2 decades after the Michelson-Morley experiment, physicists struggled to explain this bizarre result. Several brilliant minds, including the Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald, proposed mathematical fixes. They suggested that objects physically contracted in the direction of their motion, which would explain why the interferometer could not detect any difference. Their mathematics was correct, but they did not fully understand why their equations worked. They were describing the right phenomenon, but for the wrong reasons. And then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, changed everything. His name was Albert Einstein, and in a single remarkable year, he published 4 papers that would revolutionize physics. The most famous of these was titled On the Electrodynamics of Moving Bodies, and it laid out what we now call the special theory of relativity. Einstein did not have access to fancy laboratories or expensive equipment. He did not even have a university position at the time. What he did have was an extraordinary ability to think about physics in a completely new way, and the courage to follow the logic wherever it led, no matter how bizarre the conclusions. Einstein's approach was radically different from everyone who came before him. Instead of trying to explain away the constant speed of light as some weird anomaly, he embraced it as a fundamental truth about the universe and asked, if the speed of light really is constant for all observers, what does that tell us about the nature of space and time? And the answer, it turned out, was revolutionary. Einstein built his entire theory on just two postulates, two simple assumptions. The first postulate was that the laws of physics are the same in all inertial reference frames. An inertial reference frame is just a fancy way of saying any frame of reference that is not accelerating. If you are sitting in a train, moving at a constant speed in a straight line, the laws of physics work exactly the same for you as they do for someone standing still on the platform. You cannot do any experiment inside that train that would tell you whether you are moving or not, as long as the motion is smooth and constant. This postulate was not new. Galileo and Newton had said essentially the same thing centuries earlier. The second postulate was the revolutionary one. Einstein declared that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. This was the bombshell. This was what the Michelson-Morley experiment had demonstrated, and what Einstein had the audacity to accept at face value. The speed of light is not relative. It does not change depending on how fast you are moving. It is a universal constant, the same for everyone, everywhere, always. Now, these two postulates might not sound like much, but when you combine them and follow the mathematics rigorously, you arrive at conclusions that shatter our everyday understanding of reality. Because if the speed of light is constant for all observers, and if the laws of physics are the same in all inertial reference frames, then something else has to give. And what gives, what breaks, what shatters into pieces, is our intuitive understanding of space and time. Let me show you why with a thought experiment. Imagine you are on a train, and inside the train you have a special clock. This clock works by bouncing a pulse of light between two mirrors, one on the floor and one on the ceiling. Every time the light bounces off the ceiling mirror and comes back down to the floor mirror, the clock ticks once. Simple enough. Now, when you are standing inside the train, you see the light going straight up and straight down. The path of the light is a simple vertical line. You can calculate the time for each tick by dividing the distance between the mirrors by the speed of light. Everything makes sense. But now, imagine someone is standing on the platform outside, watching your train zip by at a significant fraction of the speed of light. What do they see? They see the train moving forward, which means that by the time the light reaches the ceiling mirror has moved forward a bit. And by the time the light comes back down to the floor mirror has moved forward even more. From the platform observer's perspective, the light is not traveling in a straight vertical line. It is traveling in a diagonal zigzag pattern. And here is the critical point. That diagonal path is longer than the vertical path you see inside the train. Now, remember Einstein's second postulate. The speed of light is the same for both observers. The person on the platform sees the light traveling a longer path. But the speed of light has not changed. If the path is longer, but the speed is the same, then the time must be greater. The platform observer sees your clock ticking more slowly than you do. This is not an illusion. It is not a trick of perception. Your clock actually, genuinely, physically ticks more slowly, as seen by the platform observer. Time itself slows down for you, the moving observer, relative to the stationary observer. This is time dilation, and it is one of the most counterintuitive and yet thoroughly proven phenomena in all of physics. The mathematics of time dilation are captured by a quantity called the Lorentz factor, represented by the Greek letter gamma. The formula is gamma equals 1 divided by the square root of 1 minus v, squared over c squared, where v is your velocity and c is the speed of light. When you are stationary, v is 0, and gamma equals 1. Time passes normally, but as your speed increases, gamma increases. At 10% of the speed of light, gamma is about 1.005. time dilation is barely noticeable, just 0.5% slower. At 50% of the speed of light, gamma is about 1.155. Your clock runs about 15% slower than a stationary clock. Still not dramatic, but measurable. But watch what happens as we go faster. At 90% of the speed of light, gamma jumps to about 2.294. Time for you is running at less than half the rate of time for a stationary observer. For every hour that passes on your clock, 2.29 hours pass on Earth. At 99% of the speed of light, gamma is about 7.089. For every hour that passes for you, over 7 hours pass on Earth. At 99.9%, gamma is about 22.37. 1 hour for you is almost a full day on Earth. At 99.99%, gamma is about 70.71. 1 hour of your time equals nearly 3 days on Earth. And at 99.9999%, gamma is about 707. 1 hour of your time equals almost a month on Earth. And here's where it gets truly insane. As your speed approaches the speed of light, as v approaches c, gamma does not just get big. It does not just get very big, it goes to infinity. At exactly the speed of light, gamma is infinite. Time dilation is infinite. Time has stopped. Completely. Utterly. Absolutely stopped. Let that sink in for a moment. At the speed of light, time does not slow down, it does not crawl, it stops. From the perspective of something traveling at the speed of light, time simply does not exist. There is no past, no present, no future. Everything happens simultaneously. Or rather, nothing happens at all, because happening requires the passage of time, and there is no time to pass. This is not science fiction. This is not speculation. This is what the mathematics of special relativity, one of the most thoroughly tested and confirmed theories in the history of science, tells us. And it has been confirmed experimentally in ways that are absolutely irrefutable. Consider the twin paradox, one of the most famous thought experiments in physics. Imagine two identical twins, let us call them Amara and Bilal. On their 30th birthday, Bilal boards a spacecraft capable of traveling at 90% of the speed of light. He travels to a star 10 light-years away and then turns around and comes back. From Amara's perspective on Earth, the round trip takes a little over 22 years. The distance is 10 light-years each way, and at 90% of the speed of light, each leg takes about 11.1 years. When Bilal returns, Amara is roughly 52 years old. But here's the twist. For Bilal, because of time dilation, only about 9.7 years have passed. When he steps off the spacecraft, he is roughly 40 years old. His twin sister's 12 years older than him. They started the same age, and now one of them is significantly younger. Not because of some trick or illusion, but because time itself passed at different rates for each of them. This is not a paradox at all, despite its name. There is an asymmetry between the twins. Amara stayed in a single inertial reference frame the entire time. Bilal did not. He had to accelerate, turn around, and decelerate. That acceleration is what breaks the symmetry and makes the situation non-paradoxical. The twin who travels really does age less, and this has been confirmed experimentally. In 1971, two physicists named Joseph Haffel and Richard Keating loaded extremely precise atomic clocks onto commercial airplanes and flew them around the world, once eastward and once westward. When they compared the airplane clocks to identical clocks that had stayed on the ground, they found exactly the differences predicted by relativity. The clocks on the airplanes had ticked at slightly different rates than the ground clocks. The differences were tiny, on the order of nanoseconds, because airplanes travel at only a minuscule fraction of the speed of light. But the differences were there, they were measurable, and they matched Einstein's predictions perfectly. There is an even more dramatic confirmation that happens every single second in our atmosphere. Cosmic rays from deep space slam into atoms in the upper atmosphere, creating a shower of subatomic particles called muons. Muons are unstable. They have a half-life of about 2.2 microseconds, which means that on average, they decay after just 2.2 millionths of a second. Even traveling at nearly the speed of light, a muon should only be able to travel about 660 meters before decaying. The upper atmosphere is about 10 kilometers above the Earth's surface, so the muons should all decay long before they reach the ground. But they do not. We detect huge numbers of muons at the Earth's surface. How? Because time dilation. The muons are traveling so fast, at about 99.94% of the speed of light, that time for them is running much more slowly than time for us. In their reference frame, only a fraction of a microsecond passes during their journey. They have plenty of time to reach the surface. From our perspective, their internal clocks are running slow, stretching their brief lifetimes long enough to make the trip. It is the same physics, just seen from different perspectives. And then there is the Global Positioning System, the GPS that is probably in your pocket right now. GPS works by triangulating signals from a network of satellites orbiting the Earth at about 20,000 kilometers altitude. These satellites are moving at about 14,000 kilometers per hour, and they are also in a weaker gravitational field than clocks on the ground. Both of these factors affect the flow of time. The satellite's motion causes their clocks to tick slightly slower due to special relativistic time dilation, while the weaker gravity causes them to tick slightly faster due to general relativistic time dilation. The net effect is that the satellite clocks gain about 38 microseconds per day compared to ground clocks. That might sound tiny, but if GPS did not account for these relativistic effects, the position errors would accumulate at a rate of about 10 kilometers per day. Within a week, your GPS would be so inaccurate that it would be completely useless. Every time you use GPS to navigate, you are relying on Einstein's theory of relativity being correct. And it works every single time with extraordinary precision. So, time dilation is real. It is proven. It is not a theory in the everyday sense of the word, meaning a guess or a hypothesis. It is a theory in the scientific sense, meaning it is a framework that has been tested, retested, confirmed, and verified beyond any reasonable doubt. And the implications are staggering. Because time dilation tells us something profound about the nature of reality. Time is not what we think it is. It is not a universal, constant flow that ticks along at the same rate for everyone everywhere. Time is flexible. Time is personal. Time depends on how fast you are moving and where you are in a gravitational field. Your time is not the same as my time. Right now, as you watch this video, if someone is flying overhead in an airplane, their time is passing at a slightly different rate than yours. The difference is unimaginably tiny at everyday speeds, but it is there. And at higher speeds, the difference becomes dramatic, stunning, and ultimately, as you approach the speed of light, infinite. Now, time dilation is just one of the three major consequences of special relativity. The second one is equally mind-bending, and it is called length contraction. Just as time slows down for a moving object, the length of that object, as measured by a stationary observer, contracts in the direction of motion. The formula for length contraction is L equals L0 times the square root of 1 minus v squared over c squared, where L0 is the object's rest length, v is its velocity, and c is the speed of light. At low speeds, the contraction is negligible, but at high speeds it becomes dramatic. Let us say you have a spaceship that is 100 meters long when it is sitting still. At 50% of the speed of light, that spaceship would appear to be only about 86.6 meters long to a stationary observer. At 90% of the speed of light, it would appear to be only about 43.6 meters long. At 99% of the speed of light, it would shrink to about 14.1 meters. At 99.99%, it would be a mere 1.41 meters long. A 100-meter spaceship compressed to the length of a tall person. And at the speed of light itself, the contraction is total. The spaceship would have zero length in the direction of motion. It would be infinitely thin, a two-dimensional object, a plane with no depth at all. But wait, you might say, does the spaceship actually shrink? If I am inside the spaceship, do I feel myself being crushed? The answer is no. From inside the spaceship, everything looks and feels perfectly normal. Your spaceship is still 100 meters long. Your body is still its normal size. Nothing inside the spaceship has changed at all. The contraction is only apparent to an outside observer. But here is the twist that makes your brain hurt. From your perspective inside the spaceship, it is the outside universe that has contracted. The distance between stars has shrunk. The entire universe ahead of you has compressed. If you are flying toward a star that is 10 light-years away, and you are traveling at 99.99% of the speed of light, that 10 light-year distance has contracted to just 0.14 light-years from your perspective. This is not an illusion. This is real. Space itself has changed for you. This leads to one of the most beautiful and strange insights of special relativity. Time dilation and length contraction are two sides of the same coin. They are the way the universe preserves the constancy of the speed of light. Think about it. If you are traveling at 99% of the speed of light toward a star 10 light-years away, a stationary observer would say your trip takes about 10.1 years. But for you, time is dilated by a factor of about 7, so only about 1.4 years pass on your clock. But wait, how can you cover 10 light-years of distance in only 1.4 years without exceeding the speed of light? Because from your perspective, the distance is not 10 light-years. It is contracted to about 1.4 light-years. So you travel 1.4 light-years in 1.4 years at just under the speed of light. The math works out perfectly. Relativity is self-consistent in a way that is almost eerily beautiful. The length contraction leads to some absolutely delightful paradoxes. Consider the famous ladder paradox, sometimes called the barn paradox. Imagine you have a ladder that is 10 meters long and a barn that is only 5 meters deep. Obviously, the ladder does not fit inside the barn. But now, imagine the ladder is moving at a very high speed, say 87% of the speed of light, where the Lorentz factor is about 2. From the barn's perspective, the moving ladder is length contracted to 5 meters. It fits. You could, in principle, briefly close both doors of the barn simultaneously while the contracted ladder is inside. But here is the paradox. From the ladder's perspective, it is the barn that is moving, and the barn is contracted to only 2.5 meters. The ladder definitely does not fit. So, who is right? Both of them. The resolution lies in one of the most profound consequences of special relativity, the relativity of simultaneity. Events that are simultaneous in one reference frame are not necessarily simultaneous in another. From the barn's perspective, both doors close at the same instant while the ladder is inside. From the ladder's perspective, the front door closes first, and then after the front of the ladder hits the front door and starts to come out the other side, the back door closes. The ladder is never fully inside the barn in the ladder's frame. Both descriptions are completely consistent with each other and with all the laws of physics. There is no contradiction. But the price we pay for this consistency is that we have to give up the notion that simultaneity is absolute. Two events that happen at the same time, for one observer, may happen at different times for another. Time is not just flexible in its rate of passage. The very ordering of events can depend on the observer. Now, let us come to the third major consequence of special relativity, and in some ways the most dramatic one. Relativistic mass increase. As an object moves faster, it becomes harder and harder to accelerate it further. In the language of physics, its inertia increases. Many physicists describe this by saying that the object's relativistic mass increases, although modern physicists often prefer to talk about the increase in momentum and energy rather than mass, since the rest mass of the object does not change. But the practical effect is the same. It takes more and more energy to make a fast object go even a little bit faster. The relationship is governed by the same Lorentz factor gamma. The relativistic momentum of an object is P equals gamma times m times v, where m is the rest mass and v is the velocity. At low speeds, this is essentially just P equals mv, Newton's familiar formula. But at high speeds, gamma grows, and the momentum grows much faster than you would expect from Newton's physics alone. Let us put some numbers on this. Imagine a spaceship with a rest mass of 1,000 kilograms. At 10% of the speed of light, its relativistic momentum is only about 0.5% more than what Newton would predict. No big deal. At 50% of the speed of light, its momentum is about 15% higher than the Newtonian prediction. At 90% of the speed of light, its momentum is about 2.3 times what Newton would predict. The spaceship is behaving as if it were 2.3 times as massive. At 99% of the speed of light, the effective mass is about 7 times the rest mass. At 99.99%, it is about 70 times. And at the speed of light, the effective mass would be infinite. This is the ultimate barrier. This is why nothing with mass can ever reach the speed of light. As you get closer and closer to C, you need more and more energy to accelerate even a tiny bit more. Each incremental increase in speed requires exponentially more energy. To actually reach the speed of light, you would need an infinite amount of energy. And there is not an infinite amount of energy in the entire observable universe. It is not a question of building a bigger engine or finding a better fuel. The universe itself does not contain enough energy to accelerate even a single electron to the speed of light. It is a fundamental, inviolable limit built into the fabric of reality. And this is where Einstein's most famous equation comes in. E equals mc squared. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are the same thing, just in different forms. A small amount of mass contains an absolutely staggering amount of energy. The c squared in the equation is the speed of light squared, which is about 9 times 10 to the 16th in metric units. That is an enormous number. It means that 1 kilogram of matter, if you could convert it entirely into energy, would release about 90 million billion joules of energy. That is roughly equivalent to the energy released by a 21 megaton nuclear bomb. The atomic bomb that destroyed Hiroshima converted only about 0.7 of a gram of matter into energy. Less than a paperclip's weight of matter, converted by E equals mc squared, devastated an entire city. This equation also explains why accelerating to light speed requires infinite energy. As your speed increases, your kinetic energy increases. But that kinetic energy has mass because energy and mass are equivalent. So as you gain energy, you gain mass. And as you gain mass, you need even more energy to accelerate further, which gives you even more mass, which requires even more energy. It is a vicious cycle that escalates toward infinity as you approach C. You are caught in an asymptotic trap. forever approaching but never reaching the speed of light. But photons, particles of light, do travel at the speed of light. How? Because photons have zero rest mass. They have no mass to increase. They are born at the speed of light and they die at the speed of light. They never accelerate and they never decelerate. They simply exist at c from the moment of their creation to the moment of their absorption. And from a photon's perspective, because time dilation is infinite and length contraction is total, the photon experiences no time and no distance. A photon emitted from a star on the other side of the observable universe, a photon that we measure as having traveled for 13 billion years across 13 billion light-years of space, experienced absolutely none of that journey. From the photon's perspective, it was emitted and absorbed in the same instant at the same point. Its entire existence is a single moment of zero duration. The photon has no experience of travel, no experience of waiting, no experience of time. It simply is, and then it simply is not. Now, I want to take you on the main journey, the centerpiece of this video. We are going to get in our hypothetical spacecraft, and we are going to accelerate from a standing start all the way up toward the speed of light. I want you to imagine that you are really there, sitting in the pilot seat, watching through the forward viewport as the universe transforms around you. We are going to do this step by step, and at each stage, I am going to tell you exactly what the physics says would happen. Not the science fiction version, the real version. And I promise you, the real version is far more extraordinary than anything Hollywood has ever imagined. Before we begin our acceleration, let us set the scene. You are in orbit around Earth, floating weightlessly in your spacecraft. Through the viewport, you can see the magnificent blue marble of Earth below you, the moon in the distance, and all around, the familiar stars of the night sky. Everything looks normal. Everything feels normal. Your clocks are ticking at the usual rate. Your spaceship is its full length. Your mass is your normal mass. You are in the universe as you have always known it. Now you engage the engines, and not just any engines. For this thought experiment, we are going to imagine that you have some miraculous propulsion system that can provide a constant acceleration of 1g, the same acceleration due to gravity on the Earth's surface, for as long as you want. This is convenient because at 1g, you feel exactly the same as you do standing on Earth. The floor of the spacecraft pushes on your feet with a familiar force. You can walk around, eat, sleep, and live normally. It is the most comfortable possible way to travel, and 1g of constant acceleration is actually astonishingly effective. After just 1 year of constant 1g acceleration, you would be traveling at about 77% of the speed of light. After 2 years, you would be at about 97%. After 3 years, about 99.5%. After 5 years, you would be at 99.99%. Constant 1g acceleration gets you to ludicrous speeds in a surprisingly short amount of time, at least from your perspective inside the ship. Let us begin. You push the throttle forward. The engines roar to life, or rather, in the silence of space, they hum with power. You feel yourself pressed gently into your seat with a comfortable 1g force. Earth begins to recede behind you. You are on your way. In the first few minutes, nothing seems unusual. You are accelerating, but at everyday feeling rates. A fighter jet pilot would find this boring. After 1 minute at 1g, you are traveling at about 588 meters per second, roughly Mach 1.7. Fast by everyday standards, but cosmically insignificant. After 10 minutes, you are at about 5,880 meters per second, about 21,000 kilometers per hour, faster than any commercial aircraft, but still slower than orbital velocity. After 1 hour, you are at about 35,300 meters per second, about 127,000 kilometers per hour. Now, you are moving faster than any human has ever traveled before. The Apollo 10 astronauts hold the record for the fastest speed ever achieved by humans, at about 39,897 kilometers per hour. You have just smashed that record, but you are still at only 0.012% of the speed of light. The speed of light is almost impossibly far away. After 1 day of continuous 1g acceleration, you are at about 3,048 kilometers per second, roughly 1% of the speed of light. Now, things are starting to get interesting. At 1% of the speed of light, you are covering about 263 million kilometers per day. You would cross the distance from Earth to Mars in about 4 minutes at closest approach. Jupiter is about 2 hours away. You are moving faster than anything humanity has ever built, faster than the Parker Solar Probe, faster than any particle accelerator on Earth propels macroscopic objects. But relativistic effects are still negligible at this speed. The Lorentz factor is only about 1.00005. Time dilation, length contraction, mass increase, they are all so tiny as to be undetectable without extremely sensitive instruments. After a few days, you pass through 10% of the speed of light, about 30,000 kilometers per second. Now, you are in a realm of speed that no human-made object has ever achieved, though particles and accelerators routinely reach much higher speeds. At 10% of c, a few relativistic effects start to become barely measurable if you have good enough instruments. The Lorentz factor is about 1.005, meaning time is running about 0.5% slower for you compared to Earth. Length contraction is similarly tiny. You would not notice anything different looking out the viewport. Stars would look completely normal. Space would look completely normal. You might notice that Doppler shifting is starting to become detectable. Light from stars ahead of you would be very slightly blue shifted, meaning shifted toward shorter, higher energy wavelengths. Light from stars behind you would be very slightly red shifted toward longer, lower energy wavelengths, but the shifts would be subtle, probably not visible to the naked eye. The energy requirements, however, are already staggering. Accelerating even a modest spacecraft to 10% of the speed of light requires an obscene amount of energy. If your spacecraft has a mass of, say, 100 metric tons, the kinetic energy at 10% of CE would be about 45 petajoules. That is roughly equivalent to the total energy consumption of the entire United States for about 12 hours. And that is just the kinetic energy. The actual fuel energy required would be far higher, because no propulsion system is perfectly efficient. With our current best technology, chemical rockets, reaching 10% of the speed of light is essentially impossible. Even nuclear propulsion would struggle enormously. You would need something far more advanced, perhaps antimatter engines, or some form of propulsion we have not yet invented. But in our thought experiment, we have our magical 1IG drive, so let us keep going. After about 35 days of constant 1g acceleration, you pass through 50% of the speed of light, approximately 150,000 kilometers per second, half the speed of light. You are now moving at a speed that makes our fastest rockets look like they are standing still. At this speed, you could reach the nearest star, Proxima Centauri, about 4.24 light-years away, in about 7.3 years of ship time. Still a long journey, but within a human lifetime. At 50% of c, relativistic effects are becoming noticeable. The Lorentz factor is about 1.155. Time for you is running about 13% slower than time on Earth. Your clocks show 1 p.m., while Earth's clocks show about 1:09 p.m. for the same interval. Length contraction means that from an outside observer's perspective, your 100-meter spaceship now appears to be about 86.6 meters long, and the effective mass of your ship has increased by about 15%. But the most dramatic changes are visual. The Doppler effect is now clearly visible. Stars ahead of you are noticeably blue-shifted. Stars that were normally white are now taking on a blue-white tinge. Stars that were red are now appearing orange or yellow. Meanwhile, stars behind you are red-shifting. White stars are becoming yellowish. Some of the dimmer stars behind you might be red-shifting into the infrared and becoming invisible to your naked eye. The overall pattern of stars is also beginning to shift. Stars that were to your sides are appearing to crowd forward, clustering toward the front of your field of view due to a phenomenon called relativistic aberration. The whole star field ahead of you is starting to look slightly denser, while the star field behind you is starting to thin out. There is another, more practical concern at 50% of the speed of light: collisions with interstellar material. Space is not empty. Even in the vast voids between stars, there are stray atoms, mostly hydrogen, floating around at a density of about 1 atom per cubic centimeter. That does not sound like much, but when you are traveling at half the speed of light, every atom you encounter hits you with enormous energy. At 50% of c, a single hydrogen atom impacts with the kinetic energy of about 350 million electron volts, which is comparable to the energy of a proton in a particle accelerator beam. Every square centimeter of your spacecraft's forward surface is being bombarded by these particles at a rate of millions per second. The cumulative effect is a steady stream of radiation, similar to being inside a low-power particle accelerator beam. You would need serious shielding to protect yourself and your spacecraft. Without it, the radiation dose would be dangerous over extended periods, and it is not just atoms you need to worry about. Interstellar space also contains tiny dust grains, typically a micrometer or so in size. At 50% of the speed of light, a 1 micrometer dust grain hits with an energy of about half a joule. That might not sound like much, but it is concentrated in an unimaginably tiny impact area, which means the pressure at the impact point is enormous. It is like being hit by a tiny hypervelocity bullet. Each impact would create a microscopic crater in your hull. Over time, millions of these impacts would erode and damage the spacecraft's surface. And if you hit a larger grain, say a millimeter-sized particle, the impact energy would be about 500,000 joules, equivalent to a small explosive charge. A centimeter-sized pebble would hit with the force of a substantial bomb. So, at 50% of the speed of light, your magical journey is already looking dangerous. But let us keep going, because it gets so much more extreme. After about 2 months of constant 1g acceleration, you pass through 75% of the speed of light. The Lorentz factor is about 1.51. Time for you is running about 34% slower than on Earth. Your spaceship appears to be about 66 meters long to outside observers, down from 100 meters. The star field ahead of you is now noticeably compressed and bright, while the view behind you is growing dark and sparse. After about 3 months, roughly 100 days, you pass through 90% of the speed of light. 270,000 kilometers per second. You have crossed a threshold. You are now firmly in the realm of extreme relativistic physics. The Lorentz factor is 2.294. Time for you is running at less than half the rate it does on Earth. For every hour that passes on your clock, 2.29 hours pass on Earth. Length contraction has shrunk your ship, from an outside perspective, to about 43.6 meters, less than half its original length. Your effective mass has more than doubled, and the visual effects are now extraordinary. Looking out the forward viewport, the universe has transformed. The stars ahead of you are dramatically blue-shifted. Stars that normally glow with a warm yellow light, like our sun, are now burning with a fierce blue-white intensity. Some stars that were yellow or red have blue-shifted into the ultraviolet, becoming invisible to your eyes while searing your viewport with UV radiation that could give you a sunburn in minutes if you were exposed. The entire star field has crowded forward. Stars that were off to the sides at 90 degrees to your direction of travel have shifted forward and now appear to be clustered in the forward hemisphere. Behind you, the universe is growing dark. Red-shifted stars have faded from white to yellow to orange to red to deep crimson, and some have red-shifted entirely into the infrared, disappearing from view. Directly behind you, there is a growing circle of absolute blackness where formerly visible stars have red-shifted beyond the range of human vision. And then there is something truly beautiful and eerie, the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space as microwave frequency radiation, normally invisible to the human eye, is being blue-shifted by your motion. Ahead of you, this ancient radiation is shifting from microwaves into the infrared, and at 90% of C, it is starting to creep into the visible spectrum. You might begin to see a faint, warm glow surrounding the cluster of blue-shifted stars ahead of you. A halo of light that is literally the echo of the birth of the universe, compressed and amplified by your tremendous speed. The radiation environment has become severe. Hydrogen atoms in the interstellar medium now hit your spacecraft with energies of several billion electron volts each, comparable to the energies in major particle accelerators like the Large Hadron Collider. The forward surface of your ship is being bombarded with what amounts to a particle accelerator beam. Without extremely heavy shielding, perhaps meters thick of dense material, the radiation would penetrate your hull and irradiate everything inside, including you. At these energies, the radiation would cause severe DNA damage, organ failure, and death in short order. The concept of using a physical spacecraft at this speed without extraordinary shielding is essentially a death sentence. Dust grain impacts have become genuinely catastrophic. A 1 micrometer grain now hits with about 4 joules, several times more than at 50% of C. A millimeter-sized grain carries about 4 million joules, equivalent to roughly 1 kilogram of TNT. If you hit a pebble, a grain the size of a small marble, the impact would release energy comparable to a tactical nuclear weapon. At 90% of the speed of light, even the near vacuum of interstellar space has become a lethal obstacle course. But let us keep going. We are not done yet, not by a long shot. After about 6 months of constant 1g acceleration, you approach 99% of the speed of light. The Lorentz factor is now about 7.089. Time for you is running at roughly 1/7 the rate of time on Earth. For every day that passes on your clock, a full week passes back home. Length contraction has compressed your ship, from an external perspective, to about 14 meters, barely 1/7 of its original length. Your effective mass has increased by a factor of 7. The visual transformation of the universe is now extreme and utterly alien. Almost all the stars you can see have crowded into a tight, brilliant cluster directly ahead of you. This cluster is overwhelmingly blue, with the most intensely blue-shifted stars having shifted well beyond the visible spectrum into the ultraviolet, X-ray, and even soft gamma-ray frequencies. You cannot see them with your eyes anymore, but your instruments can detect them as an intense beam of high-energy radiation concentrated in the forward direction, a phenomenon known as the searchlight or headlight effect. The few stars that are still visible to your naked eye form a brilliant, dazzling ring around a central point that is dominated by invisible high-energy radiation. It is both beautiful and terrifying. Behind you, the universe has gone almost completely dark. The vast majority of stars have redshifted so far beyond the visible spectrum that there is nothing to see. You are staring into an abyss of blackness, an emptiness so complete that it looks as if half the universe has simply ceased to exist. But it has not. It is still there. The light from those stars is still reaching you. It is just arriving as radio waves now, far too low frequency for your eyes to detect. The cosmic microwave background radiation ahead of you has now blue-shifted dramatically. What was once a faint microwave whisper from the early universe has been compressed into intense infrared and visible radiation. Ahead of you, the ancient light of the Big Bang is now a visible glow, a ring of light surrounding the central cluster of blue-shifted stars. You are literally seeing the remnant radiation from the birth of the universe, 13.8 billion years old, blue-shifted into visibility by your speed. It is one of the most poetic things that physics predicts. At sufficiently high speeds, you can see the Big Bang's afterglow with your naked eyes. The interstellar environment is now unimaginably hostile. Each hydrogen atom that hits your ship carries an energy of about 44 billion electron volts, comparable to the energy of particles in the most powerful particle accelerators on Earth. Your ship's forward surface is being subjected to a continuous bombardment equivalent to standing in front of a focused beam at the Large Hadron Collider. The radiation would kill you in seconds without shielding so massive that it might not be practically possible to build, and impacts with the dust grains. A 1 micrometer grain now carries about 220 joules of energy. A millimeter-sized grain carries about 220 million joules, equivalent to about 50 kilograms of TNT. A 1-gram speck of dust, the kind of thing you would not even notice floating through your living room, now impacts with the energy of about 80 kilotons of TNT. That is several times the energy of the Hiroshima bomb. A grain of sand hitting your ship would cause an explosion larger than a nuclear weapon. At 99% of the speed of light, you are not just a spaceship. You are a weapon of mass destruction. If your ship were to collide with a planet at this speed, the impact energy would make the asteroid that killed the dinosaurs look like a firecracker. These are the realities of near-light-speed travel that science fiction rarely addresses. The interstellar medium, which seems so empty and benign at low speeds, becomes a lethal environment at relativistic velocities. The very atoms and particles that float harmlessly through space become deadly projectiles when you are the one moving fast enough to make them dangerous. Now, let us push further still. We are entering the realm of the truly extreme. 99.9% of the speed of light. The Lorentz factor is about 22.37. Time for you is running at 1/22nd the rate on Earth. For every hour that passes on your clock, 22 hours pass on Earth. Nearly a full day for every hour. A year of your time corresponds to over 22 years on Earth. If you left Earth at age 30 and traveled at this speed for 10 years of your time, you would return to find that over 220 years had passed. Everyone you ever knew would be long dead. Entire generations would have been born and died. The world you returned to would be unrecognizably different from the one you left. Your spaceship, from an external perspective, has been compressed to about 4.5 meters in length. From the outside, what was once a sleek 100-meter vessel now looks like a flat, impossibly thin disk hurtling through space. But from inside, you notice nothing different. Your ship is still 100 meters long. Your body is still its normal shape. You can walk from one end of the ship to the other in the usual amount of time. The contraction is entirely in the eyes of external observers, and the universe you see out the viewport has become something almost unrecognizable. Virtually all the stars in the sky have been compressed into a tiny, brilliant, overwhelmingly intense point of light directly ahead of you. It is a concentration of the light of the entire visible universe, blue-shifted to extraordinary energies. Most of this radiation is now in the X-ray and gamma-ray range, invisible and lethal. The visible component is a searing, blue-white pinpoint so bright that looking at it directly would destroy your eyes instantly. Behind you and to the sides, there is nothing. Absolute, total, complete darkness. It is as if the universe contains only a single point of light, directly ahead, and an infinite void everywhere else. Let us push even further. 99.99% of the speed of light. The Lorentz factor is now about 70.71. 1 year of your time equals over 70 years on Earth. Your effective mass is 70 times your rest mass. Your ship, from the outside, appears to be only about 1.4 meters long, compressed to the height of a child. The energy required to maintain your acceleration is increasing at a horrifying rate. Each incremental increase in speed costs exponentially more energy than the last. At this speed, the universe through your viewport has collapsed into an almost unimaginably intense pinpoint of radiation ahead of you. The cosmic microwave background has been blue-shifted into the X-ray spectrum. The X-ray and gamma-ray bombardment from ahead is so intense that no conceivable material could withstand it. Your ship would be heated, irradiated, and ultimately vaporized. This is no longer a journey. This is a plunge into a wall of pure energy. Let me give you a sense of the time dilation at this speed. If you traveled at 99.99% of c for just 1 year of your time, 70.71 years would pass on Earth. When you left, your younger sister was 20 years old. When you return, she would be over 90, if she is even still alive. You missed her entire adult life. Her marriage, her children growing up, her grandchildren, everything, in what felt to you like a single year. This is not time travel in the science fiction sense with machines and wormholes. This is real, physical, experimentally verified time travel, one way into the future. And it is built into the very structure of the universe. Now, 99.9999% of the speed of light. The Lorentz factor is about 707. 1 year of your time equals over 700 years on Earth. If you left in the year 2026, traveled for a single year of your own time, and then returned, you would arrive back on Earth around the year 2733. 7 centuries would have passed. You would be an artifact from the distant past, a visitor from an era as far removed from the people of that time as the Middle Ages are from us. Civilizations may have risen and fallen. Languages may have changed beyond recognition. The Earth itself may be utterly transformed. And for you, only a year has gone by. Your spaceship, from the outside, is now about 14 centimeters long, less than the length of a pencil. A 100-meter vessel compressed to the size of a small object, not because it has physically shrunk, but because space itself is contracted from the external observer's perspective. Your effective mass is 700 times your rest mass. The energy required to accelerate you further is now inconceivably enormous. Let us go even further. 99.999999%. 8 nines. The Lorentz factor is about 70,710. 1 year of your time equals over 70,000 years on Earth. You have crossed a threshold where human civilization as we know it becomes irrelevant on the timescale of your journey. 70,000 years ago, modern humans were just beginning to spread out of Africa. If you traveled for 1 year and returned, you would come back to an Earth so different, so far in the future, that it might as well be an alien planet. And this is still not the speed of light. you are still that infinitesimal fraction below c. But the effects are already so extreme as to be almost inconceivable. And now, let us approach the final barrier. Let us talk about what happens in the ultimate, impossible, physics-breaking limit. Exactly the speed of light. At exactly the speed of light, the Lorentz factor is not just very large. It is not just enormous. It is infinite. Literally, mathematically infinite. And this means that all three consequences of special relativity, time dilation, length contraction, and mass increase reach their most extreme form. Time dilation becomes infinite. Time has not just slowed down, it has stopped. Completely, absolutely, utterly stopped. From your perspective, there is no passage of time at all. The moment you reach the speed of light is the same as every other moment. There is no after. There is no sequence of events. The concept of duration ceases to have meaning. You are frozen in an eternal, timeless now. And from the perspective of an observer on Earth, if they could somehow see you, your clock has stopped. It will never tick again. You are frozen in time, never changing, never aging, never thinking another thought. An infinite amount of time passes on Earth, and for you, not a single moment passes. Length contraction becomes total. The entire universe ahead of you, every star, every galaxy, every nebula, every atom, has been contracted to zero length in the direction of your motion. The distance from wherever you are to the most distant galaxy in the observable universe is not billions of light years. It is not millions. It is not one. It is zero. Every point in the universe along your direction of travel is at the same location. You are everywhere and nowhere simultaneously. The concept of distance, of separation, of space itself has collapsed. Mass increase becomes infinite. Your mass, however small it was to begin with, has become infinite. You are now an object of infinite mass, requiring infinite force to accelerate, infinite energy to maintain. The gravitational implications of infinite mass are paradoxical and undefined. The equations break down. Physics, as we know it, cannot handle this situation. We have reached a mathematical singularity, a point where the equations produce infinities and cease to give meaningful answers. This is what the mathematics tells us. And this is why, fundamentally, deeply, inescapably, reaching the speed of light is impossible for anything with mass. It is not that we have not built a big enough engine. It is not that we have not found the right fuel. It is not a technological limitation that will be overcome with future advances. It is a structural feature of the universe itself. The speed of light is woven into the fabric of space-time. It is the speed at which causality propagates, the speed at which information travels, the speed limit not just of light, but of everything, of gravity, of electromagnetic forces, of the strong and weak nuclear forces. It is the speed of the universe itself. And yet, here's the beautiful paradox. While nothing with mass can reach the speed of light, photons travel at exactly the speed of light, and they do so effortlessly, inevitably, always. Every photon in the universe has always traveled at exactly c, and will always travel at exactly c unless it is absorbed. Photons do not accelerate to the speed of light. They are born at that speed. They have no choice. They cannot go slower. For a photon, speed is not something achieved. It is something inherent, something essential, something that simply is. And from a photon's perspective, as we discussed earlier, time does not pass and distance does not exist. A photon emitted from a distant quasar 12 billion years ago, a photon that has been traveling across the expanding universe for the majority of cosmic history, experiences none of that journey. For the photon, it was emitted and absorbed in the same instant at the same point. Its 12 billion year journey across 12 billion light years of space was, from its own reference frame, instantaneous and distance-free. The photon connects its moment of birth to its moment of death in a single, timeless point. Some physicists caution that talking about a photon's perspective, or reference frame, is not strictly meaningful, because you cannot construct a valid inertial reference frame at the speed of light. The Lorentz transformation equations become singular. But the thought experiment, the idea of what the universe looks like in the limit as your speed approaches c, tells us something profound about the nature of light and of the universe. At the speed of light, the universe collapses. Time, space, and distance lose their meaning. The entire history of the cosmos, from Big Bang to heat death, is a single, simultaneous, zero-dimensional event. Now, I want to take a step back from the mathematics and talk about something more visceral, more immediate, more human. What would your body experience during this journey? Not just the abstract physics, but the physical, biological, tangible reality of traveling at nearly the speed of light? The first thing to understand is that speed, by itself, does not hurt you. You do not feel speed, you feel acceleration. Right now, you are moving at hundreds of thousands of kilometers per hour, relative to various things in the universe, and you feel absolutely nothing. What matters is how quickly your speed changes. This is why we chose a constant 1g acceleration for our thought experiment. It is the most comfortable possible way to get fast. At 1g of constant acceleration, you feel perfectly normal. You feel as if you're standing on the surface of the earth. You can walk around, eat, sleep, exercise. Your body functions normally. Your blood flows normally. Your organs work normally. There is no physical discomfort from the acceleration itself. In principle, you could sustain 1g acceleration indefinitely without any adverse effects on your body from the acceleration alone. But the acceleration is not the problem. The problem is everything else. As we discussed, at high velocities, the interstellar medium becomes increasingly hostile. Let me paint a more detailed picture of what this means for your body. At 50% of the speed of light, the hydrogen atoms in the interstellar medium are hitting your ship with energies comparable to particle accelerator beams. If any of this radiation penetrated your hull and reached your body, it would be similar to being irradiated in a particle physics experiment. The high-energy particles would tear through your cells, shattering DNA molecules, ionizing atoms, creating cascades of secondary radiation. The effects would be similar to acute radiation syndrome: nausea, vomiting, hair loss, immune system collapse, internal bleeding, organ failure, death. The dose rates would be extremely high, potentially delivering a lethal dose in minutes or hours depending on your shielding. At 90% of the speed of light, the radiation is even more intense. The particle energies are higher, the flux is greater, and the penetrating power of the radiation increases. You would need shielding equivalent to being inside a heavily fortified nuclear bunker, and even that might not be enough. The radiation would include not just the primary hydrogen impacts, but also secondary and tertiary radiation. Showers of pions, muons, electrons, positrons, gamma rays, and neutrons produced by the interactions of the primary particles with your shielding material. It is a radiation nightmare of enormous proportions. At 99% of the speed of light and beyond, the radiation environment is simply incompatible with life. The energies are so high that no practical amount of shielding can fully protect you. Even if you encased yourself in meters of lead or tungsten, the high-energy particles would generate cascading showers of secondary radiation that would penetrate everything. You would receive a lethal radiation dose in seconds. Your cells would be destroyed. Your DNA would be shredded. Your organs would fail. Death would come quickly and brutally. But let us set aside the radiation for a moment and imagine that you somehow have perfect shielding, some magical material that absorbs all incoming radiation without any penetrating through. Even then, you would face another problem: heat. All that kinetic energy being absorbed by your shielding has to go somewhere, and it goes into heat. At 99% of the speed of light, the energy flux hitting your forward surface is staggering. Your shielding would heat up to temperatures that would melt, then vaporize, then ionize any known material. You would need not just shielding, but active cooling systems of unimaginable capacity. The engineering challenges are not just difficult, they are likely impossible with any technology we can currently imagine. And then there are the dust grains. At near light speeds, even a microscopic dust grain hits with the force of a bomb. Your ship's hull would be subjected to a continuous barrage of hypervelocity impacts, each one potentially catastrophic. A single collision with a dust grain the size of a grain of sand could destroy your entire spacecraft. And in the interstellar medium, while dust grains are sparse, they are not absent. Over a journey of light years, you would encounter billions of them. It is like flying through a minefield at unimaginable speed, where each mine is invisible, microscopic, and carries the energy of an explosive charge. The biological conclusion is sobering. With our current understanding of physics and engineering, traveling at any significant fraction of the speed of light would be lethal. The interstellar medium that seems so empty and benign is actually a wall of death at relativistic velocities. Any real attempt at near light speed travel would require solutions to the radiation, heating, and impact problems that are currently beyond our technological capabilities. It is not impossible that future civilizations might solve these problems, but the challenges are truly fundamental. But there is another aspect of what your body would experience that I find even more profound than the physical dangers, and that is the psychological and existential dimension of extreme time dilation. Imagine that you have somehow solved all the engineering problems. You have perfect shielding, perfect cooling, a magical propulsion system. You are traveling at 99.99% of the speed of light, where the Lorentz factor is about 70, and you are on a journey that will take, let us say, 5 years of your ship time. 5 years. That is manageable, right? You can pack enough food, bring enough entertainment, stay sane for 5 years. But on Earth, during those 5 years of yours, 350 years pass. When you left, your parents were in their 60s. Your best friend had just gotten married. Your niece was starting college. When you return, they are all dead. Not just dead, but long dead. Generations have passed. Your parents, your friends, your entire social world, everyone you ever knew and loved has been dust for centuries. The language may have changed. The culture may be unrecognizable. The political boundaries, the technology, the entire fabric of human civilization has evolved beyond your recognition. You are a stranger in a strange time, displaced not through any time machine but through the simple, brutal mathematics of the Lorentz transformation. This is the true cost of near light speed travel, a cost that is often glossed over in science fiction. It is not just a physical journey, it is a one-way trip into the future. You cannot go back. Relativity gives you time travel, but only in one direction: forward. You can slow your own time relative to Earth's time, effectively jumping forward into the future. But you can never go back. The past is sealed behind you, forever inaccessible. The movie Interstellar explored this beautifully, even if it used gravitational time dilation rather than velocity-based time dilation. In that film, the astronaut Cooper lands on Miller's planet, where the extreme gravitational field near a black hole causes time to pass much more slowly. 1 hour on the planet equals 7 years on Earth. When Cooper returns to his ship after spending just a few hours on the surface, 23 years have passed on Earth. His daughter has grown from a child to a woman older than he is. The scene where Cooper watches 23 years of recorded messages from his children is one of the most emotionally devastating moments in cinema, and it is based on real physics. Time dilation is real, and the emotional consequences of it would be real too. Now, I want to shift our focus and talk about something that I find absolutely mesmerizing: what the universe actually looks like when you travel at near light speeds. We touched on this during our step-by-step acceleration, but I want to go deeper, because the visual effects are some of the most stunning and counterintuitive predictions of special relativity. At first glance, you might think that length contraction would make the universe look squished. If objects in the direction of motion are contracted, then a sphere should look like a flattened disk, right? Wrong. And the reason why is one of the beautiful surprises of relativistic physics. In 1959, the physicists James Turrell and Roger Penrose independently realized that length contraction does not actually make objects look contracted. Instead, objects moving at relativistic speeds look rotated. This is known as the Turrell-Penrose effect, or Turrell rotation. The reason is that when you look at an object, you are seeing light that left different parts of the object at different times. Light from the far side of the object left earlier than light from the near side, because it had further to travel to reach your eye. At everyday speeds, this difference in travel time is negligible, but at relativistic speeds, it matters enormously. The result is that the light you see from different parts of the object combines in a way that makes the object appear rotated rather than contracted. A sphere still looks like a sphere. A cube looks like it has been twisted around. The effect is visually stunning and completely counterintuitive, but Turrell rotation is just the beginning. The most dramatic visual effect of near-light speed travel is relativistic aberration, the way the apparent positions of stars shift due to your motion. This effect is analogous to the way that raindrops, which are falling vertically, appear to come at you from in front when you run through the rain. When you are moving very fast, the light from stars that are actually beside you or even behind you appears to come from ahead of you. Stars crowd forward toward your direction of travel. At 50% of the speed of light, a star that is actually at 90 degrees to your direction of motion, directly to your side, appears to be at about 60 degrees from your forward direction. Stars that were behind you appear to have moved forward. The overall effect is that stars cluster toward the front of your field of view. At 90% of the speed of light, a star at 90 degrees appears to be at only about 24 degrees from forward. Almost all the stars in the sky have crowded into the forward hemisphere. Behind you, the sky is growing empty. At 99% of the speed of light, a star at 90 degrees appears to be at about 8 degrees from forward. Virtually all the stars in the sky are concentrated in a small cone around your direction of travel. At 99.99%, a star at 90 degrees appears to be at about 0.8 degrees from forward. Essentially, all the light in the universe has been compressed into a tiny, brilliant point directly ahead of you. Combined with the Doppler effect, which blue shifts the light ahead of you and red shifts the light behind you, and the searchlight effect, which concentrates the energy of the light forward, the visual experience at near light speed is utterly extraordinary. Ahead of you, you see an intensely bright, blue-shifted concentration of all the universe's light, a cosmic headlight of unimaginable brilliance. Behind you, absolute darkness. It is as if you are flying into a single point of pure radiance surrounded by an infinite abyss. Computer simulations of what this would actually look like have been created by several research groups, including teams at MIT, the Australian National University, and the University of Tübingen in Germany. These simulations show a mesmerizing visual transformation. As your speed increases, the familiar constellations distort, warp, and ultimately dissolve into an increasingly concentrated ring of light that narrows and brightens as you approach C. The colors shift through the spectrum, from red to yellow to white to blue, and eventually into the ultraviolet, leaving only a residual visible ring around an intensely bright core. It is alien, it is beautiful, and it is what the real universe actually looks like at extreme speed. One particularly enchanting aspect of these simulations is what happens to the cosmic microwave background radiation. This radiation permeates all of space at a temperature of about 2.725 Kelvin, corresponding to microwave frequencies far below the visible spectrum. You cannot see it, but as you accelerate, the Doppler effect blue shifts it. At around 50 to 60% of the speed of light, the CMB ahead of you shifts into the far infrared. At around 90%, it enters the near infrared, and somewhere between 90 and 95% of the speed of light, it shifts into the visible spectrum. You begin to see the cosmic microwave background as a warm glow surrounding the cluster of blue-shifted stars ahead of you. You are seeing the afterglow of the Big Bang, the oldest light in the universe, made visible by your speed. It is a profound and humbling sight that connects you directly to the birth of the cosmos itself. Now, I want to address something fundamental. We have been talking about why nothing with mass can reach the speed of light, but I want to go deeper. I want to explain why the speed of light is the cosmic speed limit, and what would happen conceptually and physically if something could somehow break that limit. The speed of light is not just the speed at which light travels. It is better understood as the speed of causality. It is the maximum speed at which any cause can produce an effect. It is the maximum speed at which information can travel from one point to another. When we say that nothing can go faster than light, we are really saying that no influence, no signal, no information, no causal connection can propagate faster than c. This is not just an arbitrary rule. It is deeply connected to the structure of space-time and the nature of cause and effect. To understand why, let us think about space-time diagrams, a tool invented by Hermann Minkowski that provides a visual way to understand special relativity. A space-time diagram plots space on the horizontal axis and time on the vertical axis. Your position at any moment is a point on this diagram, and as you move through time, your point traces out a line called your world line. If you are stationary in space, your world line is a vertical line going straight up. You are moving through time, but not through space. If you are moving through space at a constant velocity, your world line is a tilted line. You are moving through both space and time. Now, on this diagram, light travels at a 45-degree angle, because we choose our units so that 1 unit of time corresponds to 1 unit of space traveled by light. This means that light from any event traces out lines at 45 degrees in all directions, forming a shape called the light cone. The light cone divides space-time into 3 regions. The interior of the future light cone contains all events that the original event can influence, all the places that a signal from that event, traveling at or below the speed of light, can reach. The interior of the past light cone contains all events that could have influenced the original event. And the exterior of both cones, the region outside the light cone, contains events that have no causal connection to the original event whatsoever. They cannot affect it, and it cannot affect them. They are causally disconnected. Any path that a massive object can take must stay within the light cone. It can never cross the 45-degree line, because that would mean it is traveling faster than light. Its world line is always steeper than 45 degrees, meaning it is always traveling slower than c. This constraint is not just a speed limit, it is a causality limit. It ensures that causes always precede their effects, that the arrow of time always points in one direction, that the universe makes logical sense. Because here is what would happen if something could travel faster than light. If an object or a signal could move faster than c, it would trace a path on the space-time diagram that goes outside the light cone. And here is the devastating consequence. In some reference frames, that path would appear to go backward in time. Let me explain. One of the consequences of special relativity is that observers in different reference frames disagree about the order of events that are separated by space-like intervals, meaning events that are too far apart in space for light to travel from one to the other in the time between them. If event A and event B are space-like separated, some observers will see A happening before B, others will see B happening before A, and still others will see them as simultaneous. This is the relativity of simultaneity, and it is a perfectly well-established feature of our universe for events that cannot causally affect each other. But if faster-than-light travel were possible, you could connect causally related events that are space-like separated, and that means you could set up a situation where a message is received before it was sent. This leads directly to time travel to the past, causal loops, paradoxes, and logical contradictions. The most famous of these is the grandfather paradox. You could send a signal back in time that prevents your own birth, which means you never existed to send the signal, which means the signal was never sent, which means you were born after all, which means you do send the signal, and so on in an infinite, irresolvable paradox. This is sometimes called the tachyonic antitelephone. If you could build a communication device that sends messages faster than light, then by using two such devices, one moving relative to the other, you could construct a system that sends messages into the past. This is not a vague philosophical objection. It is a rigorous mathematical consequence of special relativity combined with faster-than-light signaling. FTL communication does not just mean faster messaging. It means time travel, paradoxes, and the breakdown of causality itself. This is why physicists are so confident that the speed of light really is an absolute, unbreakable limit for information and causal influence. It is not because they lack imagination. It is because the alternative, a universe where faster-than-light communication is possible, is a universe where cause and effect break down, where the past can be changed, where logical paradoxes can actually occur. And our universe does not seem to be that kind of universe. Every experiment ever conducted, every observation ever made, is consistent with the speed of light being an absolute, inviolable limit. But wait, you might say, what about quantum entanglement? Surely that is faster-than-light communication. This is one of the most common misconceptions in popular science, and it is worth addressing carefully. Quantum entanglement is the phenomenon where two particles become correlated in such a way that measuring a property of one particle instantly determines the corresponding property of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, and he was deeply uncomfortable with it. If you measure the spin of one entangled electron and find it is up, the other electron's spin instantly becomes down, even if it is on the other side of the galaxy. It does look, at first glance, like information is being transmitted instantaneously across vast distances, far faster than light. But it is not. The key insight is that you cannot control the outcome of your measurement. When you measure your electron's spin, you get a random result, either up or down with equal probability. You cannot choose which result you get. So, while the other electron's spin does indeed become correlated with yours, the person at the other end has no way of knowing that you have made a measurement until they receive a classical, slower than light signal from you telling them so. No information, no message, no causal influence has traveled faster than light. The correlations are real, but they cannot be used to communicate. This was rigorously proved by the no-communication theorem in quantum mechanics. Einstein, Podolsky, and Rosen raised this issue in their famous 1935 paper, which became known as the EPR paradox. They argued that either quantum mechanics was incomplete, there were hidden variables determining the outcomes in advance, or nature allowed non-local influences. In 1964, the physicist John Bell devised a set of inequalities, Bell's inequalities, that could distinguish between these possibilities. Numerous experiments since then, most notably the 2022 Nobel Prize-winning experiments by Alan Aspect, John Clauser, and Anton Zeilinger, have consistently shown that Bell's inequalities are violated, ruling out local hidden variables. Nature is indeed non-local in some sense, but crucially, this non-locality cannot be exploited to send information faster than light. The universe seems to have a deep, built-in protection mechanism that preserves causality even in the bizarre world of quantum mechanics. There's actually a wonderful way to think about this. The physicists Juan Maldacena and Leonard Susskind proposed in 2013 a conjecture known as ER equals EPR. They suggested that quantum entanglement, EPR pairs, might be equivalent in some deep sense to wormholes, Einstein-Rosen bridges. If this conjecture is correct, then the spooky connections between entangled particles are literally tiny wormholes connecting them. But these wormholes, like the macroscopic wormholes of general relativity, cannot be used to transmit information faster than light. The connection is there, but it is not traversable in any way that would violate causality. It is a tantalizing hint that the speed of light limit might be woven into the fabric of reality at an even deeper level than we currently understand. Now, having firmly established that the speed of light is an absolute limit, I want to do something that might seem contradictory. I want to talk about all the ways that physicists have imagined getting around this limit. Because while the speed of light is an absolute limit for moving through space, there are some fascinating loopholes, and scientists are actively studying whether any of them might work. The first and most important loophole is this. While nothing can move through space faster than light, space itself has no speed limit. The fabric of space-time can stretch, compress, and deform at any rate, and it does. Right now, the universe is expanding, and distant galaxies are receding from us due to this expansion. The farther away a galaxy is, the faster it appears to recede. And beyond a certain distance, called the Hubble radius, galaxies are receding from us at faster than the speed of light. Yes, you read that right. There are galaxies right now that are moving away from us faster than light. This does not violate special relativity because the galaxies are not moving through space faster than light. Rather, the space between us and them is expanding so fast that the total recession velocity exceeds c. The distinction is subtle but crucial. Special relativity says nothing can move through space faster than light. It says nothing about the rate at which space itself can expand or contract. This loophole is the basis of one of the most exciting concepts in theoretical physics, the Alcubierre warp drive. In 1994, the Mexican physicist Miguel Alcubierre published a remarkable paper. He showed that the equations of general relativity, Einstein's theory of gravity and space-time, allowed for a configuration of space-time that would enable faster-than-light travel without actually moving through space faster than light. The concept is beautifully simple in principle. Instead of accelerating the spacecraft to light speed, you would deform the space-time around it. You would contract the space in front of the spacecraft and expand the space behind it. The spacecraft sits in a bubble of flat, normal space-time. It is not moving through space at all. But the bubble itself is moving, carried along by the deformation of space-time, and the bubble can move at any speed, including faster than light, because it is space-time itself that is moving, not the spacecraft. Inside the warp bubble, everything would be perfectly normal. No time dilation, no length contraction, no relativistic mass increase, no radiation bombardment. You would be sitting in calm, flat space-time, sipping tea, while the universe flows past you at many times the speed of light. You would not feel any acceleration because you are not accelerating. You are stationary. It is the space around you that is changing. It sounds too good to be true, and in many ways it is. The Alcubierre warp drive has several enormous problems. The first and most fundamental is that it requires exotic matter, matter with negative energy density. Normal matter has positive energy density. It is what makes gravity attractive. To create the warp bubble, you would need matter that has the opposite effect, matter that gravitationally repels rather than attracts, matter with negative energy. We do not know if such matter exists. There are some quantum phenomena, like the Casimir effect, where tiny amounts of what could be interpreted as negative energy appear between closely spaced conducting plates. But the amount of negative energy required for a warp drive is staggeringly large. In Alcubierre's original paper, the energy requirements were equivalent to the mass energy of Jupiter, all of it in negative energy form. That is an absurd amount of energy, negative or otherwise. However, subsequent research has reduced the energy requirements significantly. In 2011, Harold "Sonny" White, a physicist at NASA's Johnson Space Center, published a revised analysis suggesting that by optimizing the shape of the warp bubble, the energy requirements could be reduced by many orders of magnitude, potentially to something on the order of hundreds of kilograms of exotic matter equivalent, still enormously challenging but no longer obviously impossible. In 2012, White's team even set up a very small-scale experiment, using a modified Michelson interferometer to try to detect tiny space-time distortions that might indicate warp-like effects. The experiment was essentially a proof of concept, testing whether the measurement technique could work rather than actually trying to create a warp bubble. So far, no positive results have been announced, but the fact that NASA was willing to fund even a preliminary experiment suggests that the idea is taken at least somewhat seriously. In 2021, the physicist Eric Lentz published a paper proposing what he called a soliton solution that would enable warp-like travel without requiring exotic matter at all, using only positive energy densities. If correct, this would remove the biggest theoretical obstacle to the warp drive. However, the energy requirements in Lentz's solution are still enormous, equivalent to the mass energy of a substantial fraction of the Sun for a ship-sized bubble. And many physicists remain skeptical about whether such solutions truly work when examined closely. There are other problems with the Alcubierre drive, too. The interior of the warp bubble is causally disconnected from the bubble wall. This means that the occupants of the spacecraft cannot control the bubble. They cannot steer it, slow it down, or stop it. The bubble is essentially a self-contained, uncontrollable moving space. How do you initiate the warp? How do you specify the destination? How do you stop when you get there? These are not just engineering challenges. They are fundamental theoretical problems that do not currently have solutions. Additionally, some calculations suggest that the front edge of the warp bubble would accumulate an enormous amount of high-energy radiation as it sweeps up photons and particles from the interstellar medium. When the bubble collapses at the destination, all this accumulated energy would be released in a devastating burst, potentially destroying anything at the destination. You would arrive at your target star system and immediately obliterate it with a blast of radiation. Not ideal for exploration or colonization. And finally, there are serious concerns about whether the warp drive could be used to create causal paradoxes. If you can travel faster than light using a warp drive, and if the no-signaling arguments we discussed earlier still apply, then the warp drive might enable time travel to the past, with all the paradoxes that entails. Some physicists have argued that the laws of physics would somehow prevent the formation of closed, time-like curves, even with a warp drive, perhaps through a chronology protection conjecture similar to the one proposed by Stephen Hawking. But this remains an open question. The second major theoretical loophole for faster-than-light travel is wormholes, also known as Einstein-Rosen bridges. A wormhole is a hypothetical tunnel through space-time that connects two distant points. Instead of traveling the long way through normal space, you would enter one end of the wormhole and exit the other end, which could be light years or even billions of light years away. The journey through the wormhole could be arbitrarily short, even if the normal space distance between the endpoints is enormous. Wormholes emerge naturally from the mathematics of general relativity. In 1935, Einstein and his colleague Nathan Rosen showed that the equations allowed for bridges connecting different regions of spacetime. However, the Einstein-Rosen bridges in their original formulation were not traversable. They pinched off too quickly for anything, even light, to pass through them. They were mathematical curiosities, not physical pathways. In 1988, the physicists Kip Thorne and Michael Morris showed that it might be possible to create a traversable wormhole, one that a human could actually pass through if you could line the throat of the wormhole with exotic matter. There it is again, that pesky exotic matter with negative energy density. Without it, the wormhole would collapse before anything could pass through. With it, the wormhole could be held open, potentially allowing travel or communication between distant points. The problems with wormholes are similar to those with warp drives. We do not know if exotic matter exists in the quantities required. We have never observed a wormhole. We have no idea how to create one. And even if we could create one, the energy requirements would be absurd. Furthermore, Thorne showed that a traversable wormhole could, in principle, be used as a time machine by moving one end of the wormhole at high speed or placing it in a strong gravitational field, exploiting time dilation to create a temporal offset between the two ends. This, again, raises the specter of causal paradoxes. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics would conspire to prevent the creation of closed, time-like curves, even if individual components like wormholes or warp drives seem to allow them. Perhaps quantum effects would destroy a wormhole as soon as it developed a temporal loop. Perhaps some as yet unknown physical law prevents the configuration. We do not know. It remains one of the great open questions in theoretical physics. There are other more speculative ideas for faster-than-light travel. The Krasnikov tube is a concept in which a spacecraft traveling at near-light speed modifies the spacetime along its path, so that the return trip can be made faster than light. It is similar in spirit to the warp drive, but with a different geometry. Like the warp drive, it requires exotic matter and has significant theoretical problems. Then there are tachyons, hypothetical particles that always travel faster than light. In the mathematics of special relativity, if you plug in a velocity greater than c, the Lorentz factor becomes imaginary, meaning it involves the square root of a negative number. This has led some physicists to speculate about particles with imaginary rest mass that would always travel faster than light. Such particles would have bizarre properties. They would lose energy as they speed up and gain energy as they slow down. They could never be decelerated to the speed of light because that would require infinite energy. just as accelerating a normal particle to light speed requires infinite energy. They would be permanently superluminal. If tachyons existed, they could potentially be used for faster-than-light communication, which, as we discussed, would enable sending messages into the past. This is a strong theoretical argument against their existence. Despite extensive searches, no tachyon has ever been detected. Most physicists believe they do not exist, and that their appearance in the mathematics is a consequence of the equations rather than a prediction of real particles. There is one more fascinating concept I want to mention, and it is the idea that the speed of light might not be truly constant. The vast majority of experimental evidence supports the constancy of c with extraordinary precision. Tests of Lorentz invariance, the fundamental symmetry underlying special relativity, have been conducted to incredible accuracy, and no violations have been found. But a few physicists have explored the possibility that c might have been different in the very early universe, or that it might vary slightly at extremely high energies. The most prominent advocate of this idea is the Portuguese physicist João Magalhães, who has proposed what he calls the variable speed of light cosmology. The idea is that in the very first moments after the Big Bang, the speed of light might have been much faster than it is today. If true, this could solve several puzzles in cosmology, most notably the horizon problem, the question of why the cosmic microwave background is so uniform, even though opposite sides of the sky should never have been in causal contact if c has always been the same. The inflationary theory, currently the dominant explanation for the horizon problem, proposes that the universe underwent a brief period of exponentially rapid expansion in its earliest moments. Magalhães' variable speed of light theory offers an alternative explanation. The speed of light was fast enough in the early universe that the currently disconnected regions were once in causal contact. However, the variable speed of light theory is controversial and not widely accepted by the physics community. The experimental evidence for a constant EC is overwhelming, and inflationary cosmology has successfully explained the horizon problem along with several other cosmological puzzles. Still, the idea that c might not be eternal and immutable is a fascinating one, and it reminds us that even the most fundamental constants of physics are subject to scientific scrutiny and investigation. Now, let us come back down to Earth, or rather, let us look at what humanity is actually doing right now to push the boundaries of speed. Because while reaching the speed of light is impossible, and even getting close to it is fantastically difficult, we are not giving up. Not by a long shot. The fastest human-made object, as of the latest data, is the Parker Solar Probe, a NASA spacecraft that is swooping closer to the Sun than any previous mission. At its closest approach to the Sun, the Parker Solar Probe reaches speeds of about 692,000 kilometers per hour, or about 192 kilometers per second. That is roughly 0.064% of the speed of light. Incredibly fast by human standards, but still less than 1,000th of c. At that speed, it would take about 6,600 years to reach the nearest star, Proxima Centauri. Before the Parker Solar Probe, the record for the fastest human-made object was held by the Helios probes, a pair of spacecraft launched in the 1970s to study the Sun, which reached speeds of about 252,000 kilometers per hour. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object, at about 24 billion kilometers from Earth, but it is traveling at only about 61,000 kilometers per hour, a leisurely pace compared to the Parker Solar Probe. At Voyager's current speed, it would take about 73,000 years to reach Proxima Centauri. These numbers make it clear that with current chemical rocket technology, interstellar travel within a human lifetime is not merely difficult, but essentially impossible. Even the fastest spacecraft we have ever built would take millennia to reach the nearest star. We need fundamentally different propulsion technologies. One of the most exciting real projects aimed at interstellar travel is Breakthrough Starshot, funded by the late Israeli-Russian entrepreneur Yuri Milner, and backed by a team of world-class scientists and engineers. The concept is elegant. Instead of trying to accelerate a large, heavy spacecraft, you launch a tiny spacecraft, a starship, weighing just a few grams, attached to a light sail a few meters across. On the ground, you build an enormous array of lasers that can focus a powerful beam on the sail. The laser beam pushes the sail, accelerating the tiny probe to about 20% of the speed of light within minutes. At that speed, the probe would reach Proxima Centauri in about 20 years. 20% of the speed of light. That is 60,000 kilometers per second, or about 216 million kilometers per hour. It is thousands of times faster than any spacecraft in existence, and it is within the realm of engineering possibility, at least in principle. The laser array would need to be enormously powerful, on the order of 100 gigawatts, and there are significant challenges with keeping the beam focused over the enormous distances involved, with the sail surviving the intense acceleration, with communicating data back from the tiny probe across 4 light-years of space, and with the probe surviving the interstellar environment at 20% of C. But the Breakthrough Starshot team believes that none of these challenges are fundamental showstoppers, and they are working toward making the concept a reality. If Breakthrough Starshot succeeds, it would be one of the greatest achievements in the history of human exploration. For the first time, we would send an emissary to another star system. The probe could photograph any planets orbiting Proxima Centauri and send the images back to Earth, a journey that would take another 4.24 years at light speed. We might see the first close-up images of an exoplanet within the lifetimes of people alive today. Beyond Breakthrough Starshot, there are numerous other propulsion concepts that have been proposed and studied. Ion drives, which accelerate ions using electric fields and expel them for thrust, are already in use on several spacecraft, including NASA's Dawn mission that explored Vesta and Ceres. Ion drives are much more efficient than chemical rockets, but they produce very low thrust, meaning they take a very long time to achieve high speeds. Even the most advanced ion drives would take thousands of years to reach the nearest star. Nuclear pulse propulsion is a concept dating back to the 1950s in the Project Orion study. The idea is simple and somewhat terrifying. You detonate nuclear bombs behind your spacecraft, and the explosions push you forward. A large plate at the back of the ship, called a pusher plate, absorbs the impulse from each explosion and transfers it to the spacecraft. The performance of such a system would be spectacular by current standards. Calculations suggest that a nuclear pulse spacecraft could reach about 5 to 10% of the speed of light, enough to reach the nearest star in perhaps 40 to 80 years. However, the concept was never pursued beyond the study phase, in part because the Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear explosions in space, and in part because, well, writing a series of nuclear explosions is not exactly safe or environmentally friendly. Antimatter propulsion represents the theoretical peak of what chemical-style propulsion could achieve. When matter and antimatter annihilate each other, they convert 100% of their mass into energy according to E equals mc squared. This is the most efficient fuel conceivable. 1 gram of antimatter annihilating with 1 gram of normal matter would produce about 180 terajoules of energy, equivalent to about 43 kilotons of TNT. A few kilograms of antimatter could propel a spacecraft to a significant fraction of the speed of light. The problem is production and storage. Currently, we can only produce antimatter in particle accelerators, in incredibly tiny amounts. CERN, the European Organization for Nuclear Research, produces on the order of tens of nanograms of antimatter per year. To fuel an interstellar spacecraft, you would need kilograms. Producing that amount with current technology would cost more than the entire GDP of the planet and take billions of years. And storing antimatter is equally challenging, because it annihilates on contact with any normal matter. You would need to contain it in a perfect vacuum using magnetic fields, a technology that exists in primitive form, but is nowhere near the scale required for propulsion. The Bussard ramjet, proposed by the physicist Robert Bussard in 1960, is another fascinating concept. The idea is that instead of carrying your fuel with you, you scoop it up from the interstellar medium as you go. A vast magnetic funnel, hundreds or thousands of kilometers across, would collect the sparse hydrogen atoms floating in interstellar space, funnel them into a fusion reactor, and use the fusion energy for propulsion. In principle, this would give you an unlimited fuel supply, allowing continuous acceleration to very high speeds. In practice, however, subsequent analyses have shown that the magnetic scoop creates enormous drag that likely exceeds the thrust, especially at higher speeds. The interstellar medium is so sparse that you would need to sweep an enormous volume of space to collect meaningful amounts of fuel. The concept, while elegant, is probably not workable as originally conceived. Solar sails represent one of the most proven and promising near-term technologies for interstellar travel. The Japanese Ikaro spacecraft, launched in 2010, successfully demonstrated solar sailing in interplanetary space. The breakthrough starshot concept extends this idea to its extreme, using laser beams instead of sunlight to provide vastly more power and thrust. Other variations include using the solar wind or magnetic fields instead of or in addition to light pressure. Looking further into the future, there are even more speculative propulsion concepts. Fusion drives using either deuterium-tritium, deuterium-deuterium, or proton-boron fusion could in principle provide the high specific impulse needed for interstellar travel. Several organizations, including the Tau Zero Foundation and the Initiative for Interstellar Studies, are actively researching fusion propulsion for interstellar missions. The British Interplanetary Society's Project Daedalus and its successor, Project Icarus, have studied designs for unmanned fusion-powered spacecraft that could reach the nearest stars within a human lifetime, albeit at a small fraction of the speed of light. The bottom line is that while reaching the speed of light is impossible, and getting close to it is extremely difficult, traveling at a few percent to perhaps 20% of the speed of light may be achievable, perhaps within the next century, with technologies that are either currently in development or on the foreseeable horizon. This would reduce interstellar travel times from millennia to decades, bringing the nearest stars within reach for the first time. Now, I want to return to the realm of pure physics and explore some of the most beautiful and mind-bending paradoxes that arise from special relativity. We have already discussed the twin paradox and the ladder paradox, but there are several more that illuminate the strangeness of a relativistic universe. The Bell spaceship paradox is one of my favorites because it reveals a deeply counterintuitive aspect of length contraction. Imagine two identical spaceships connected by a taut string. Both spaceships start from rest and accelerate identically, simultaneously in the same direction. The question is, does the string break?